Hey everyone, this should be a fun little short lecture discussion. The goal really is to introduce a couple ideas. One is this idea of p-hacking, which is sort of hacking a p-value. Another aspect of this is to discuss this from the perspective of why cross-validation works. It also addresses why the case where you have a larger number of rows than columns is very different than when you have a larger number of columns than rows. So you may have come to this lecture from any of those directions, but it's worth kind of just walking through this. This is just a quick demonstration. And so what we're going to do is not try to produce any rigorous theory, but rather really just show you using, NumPy and not even matplotlib. Today we won't even get to any plotting, but just NumPy to discuss what's going on here. So we're going to set up NumPy as normal. We'll create our matrix M, that's our data, our X, using a random initialization, random integers through 100. And we'll get 100 examples with 3 columns of data. So if we plot this out, we can look at M and see that M has 100 rows and 3 columns. And if we look at M, we can see that its numbers roughly appear to be between 0 and 100. Okay. So now what we can do is we'll do the same thing with L. We'll have a labels. Again, labels stands for values between 0 and it will be probably 99, in fact. Won't fully reach 100. And now all we're going to do is we're going to look to see how correlated each of the columns in M is with L. That is, we take each of the column indices. So for each entry in the shape, 1, 0, 1, and 2 for the column index. We'll go and we'll use the NP calculate the correlation coefficient, and we'll pass in all of the rows for the first column of M, in this case would be the 0th, and compare it to L, the labels. And again, if you just looked at the correlation matrix, it's a correlation matrix, so we'll just take the value that we want here at the end. And if we run this, we can see that RET has a small amount of correlation there. We've got a value of 0.003, a value of 0.26. That's a pretty big correlation. A value of 0.097, so around 10% negative. Again, not a huge amount of correlation, but a little bit. And this one is only by chance. In fact, this is the largest number that I've seen when I was designing this lecture, so that's kind of interesting. And what we'd like to do is instead imagine that we aren't working with just only 100 examples, right? The classic example of calculating a p-value is if you get more rows of data, more examples, then the confidence that you're seeing something new should be, or you're seeing a real relationship should go up. And so in this case, we'll go and we'll create a random value with 1,000 values rather than just the 100 that we started with. And now if we look at M, we'll see the shape is a 1,000 rows by 3 columns. And now if we do the same things to calculate the correlation, we see that the values have gone down. You see we're at 0.01, 0.004, 0.03. So the relationship is showing that in fact there is no real relationship. We know this because it's all random between any one of the columns and our label. And just to make this even more clear, let's jump it up to not 1,000 rows of data, but let's make it 10,000. And unsurprisingly, our values actually decrease again, 0.004, 0.002, 0.001. So very small numbers, and we can expect that would continue on. And this is the principle for calculating a p-value. Is the stronger the relationship, the stronger the correlation between one column and your labels. If it's a very strong relationship, then you don't need a lot of rows of data. But if it's a weak relationship, you need more rows of data to be confident that that relationship holds. So the next question we want to ask is what happens if we change that scenario? What if we move from thinking about 1,000 rows, right, or 10,000 rows? This is where we have a skinny and tall matrix. And instead we want to think about a short and fat matrix. That's a matrix where we have still only 100 rows, but now instead of having 3 columns, we have 3,000. And so what we'll do here is we'll create this matrix. And if we look at shape, we see that it is indeed 100 rows with 3,000 columns. And if we were to look at M, just convince ourselves, looks like it's all fine. And now we will calculate the same correlation. And now if we were to look at ret, we'd see a whole bunch of values. Of course, what we really care about is the highest positive correlation and the highest negative correlation. That is, I want to know the columns that are very correlated or sort of anti-correlated with, or positively or negatively, with our value. So what we're going to do is we're going to sort our value, sort our list. And we can look at, if we want, the top 25 entries. And these will be the values. And you can see instantly, this is a much higher value. Here we've got a 0.31. That's 30% negatively. And if we were to wanted to get instead the reverse, that is the highest correlation, we'd see that the highest correlation right here is 0.357. So we have columns here that are correlated directly with our data. That is, if I look at my matrix, which is 100 by 3000, and I pull out the columns, I ask the question, doing my normal sort of scientific work, which of the columns is correlated with my outcome? That is my labels. Just by chance alone, in a purely random situation, we can expect that there will be correlations that are there that are actually really quite high. And this is just because we're getting multiple draws. Each new column of M has some probability chance of being highly correlated with L by chance alone. And if you place a whole bunch of columns, right, if we continued this out and made these numbers much larger, we'd run into even more highly correlated columns that were only there by chance. So this is really the question that we addressed ourselves with, and this is why this is the case where there are more columns than there are rows. The answer is there really isn't a correlation matrix that you can calculate that you can have confidence in. We don't have a statistical power value testing, a way of testing whether or not these correlations are real or whether they're really according to chance. So what do? This is really where cross-validation comes in. So if one might assume that since some of these relationships are built only by chance alone, that our algorithms would learn something would learn something from them and then would make decisions on this sort of fictitious data. And cross-validation was introduced as a way of addressing this issue. So what we're going to do is we'll bring in just a, plain Jane random forest classifier. And then we will create a classification, right? An instance, a CLF. And then we're going to train on the first 80% of our data. We're not even going to do the full cross-validation. We're just going to do a training and a testing split. And so we're going to take the matrix, all of the rows 0 through 80, and all of the columns, and the same thing for L. Takes just a second, and we've run. And then we'll do the same thing. We'll bring in the accuracy score to calculate how often we're correct. And if we run this, we see that our accuracy, in fact, is 0. That is, our model we've trained through has determined that there is absolutely nothing. There is no ability. None of the training that we worked on in this random data set was able to generalize from the first 80% to the last 20%. That's wonderful. Our model, of course, has learned something, but it hasn't learned the wrong thing. So let's just take a moment and look at this. So if we look at our prediction, we can see that our prediction has a whole bunch of values, right? We want to make sure that things are actually working correctly and we actually predicted something. And then we can do the same thing and check our labels, and we can see that not only was our algorithm incorrect, it wasn't even close. 70, 29, 24. These numbers are very far apart, which is, again, reassuring because we wouldn't expect it to be particularly good at predicting a random distribution. That would be a big problem if it wasn't. So if you've worked in deep learning, you're interested in deep learning, this is really, in our case, we're sort of treating this testing set of the 80 through 100 values as a validation test to calculate the accuracy, the true accuracy. But you might like to confirm that the model actually learned something. Well, I'd like to know, does the model think it's right? That is, when I look at the prediction over the first 80 values, does the model think, how well does the model do fitting and learning the processes that are going on in that 3000? So I can check my accuracy score. And you can see here on the model prediction, on my training data, the accuracy was 100%. And this is one of the purest definitions of what we would refer to as overfitting. That is, when your training error is 0, you're effectively 100% correct on your training, but your error on the validation set, or in this case what we might call the testing set, is perfect. It's completely incorrect. So when you have one that's perfect, you've learned exactly what you've been presented in M and how to learn it for L. But when you move on to the out of sample data, you fail completely. And just, for clarification, we might want to think perhaps the algorithm's not capable of learning something like a classification, because that's a little bit that can pose different problems than perhaps a regression. But if we do the same thing and work through a regressor, this will take just a second, we see that the R2 score, right, is vastly, right? It's negative 75. It's far, far, far away from what it would have predicted. And if we go to look to see what our values should be, we see predicting on those 80. We get these as the predictions, and we look at our L, and we see our L is in fact, again, huge separation between what the values should be and where we would expect them to. So it doesn't look, this algorithm certainly doesn't look like it's doing anything and working from this random data, which again is reassuring. So the key point that I'm trying to make here is twofold. One, when we move from a framework where we have a larger number of rows to columns, the normal notions that we have about how statistics should sort of hold and how relationships between your data matrix and your labels may in fact be very different than what you have been exposed to before. That is, it's very likely when you move to a scenario where there are many new rows of data and a smaller number of, many new columns of data and a smaller number of rows, that there will be relationships that occur strictly by chance. And for this reason, we use tools from this sort of statistical machine learning branch, the work that has been going on for the last 15 or 20 years, really to identify and understand how to make sense or learn from data that's of this shape. Again, more columns than rows. And one of the main reasons we can't use the traditional tools is because, again, these correlations occur on a single column by chance alone, but cross-validation provides us, given we have enough data and we have an appropriate setup, gives us the opportunity to ask, how well is it likely for our algorithm that's been trained on some data that's in sample, how likely is it going to generalize to new data, that is, data that it has not seen? And that's really the principle behind cross-validation. How the justification is, if my model works well on the data that I can show it now, assuming that the process is stable and it hasn't changed, it should do well on data that it has not yet seen. And that's the sort of theoretical justification. And in practice, it works particularly well. And in fact, in this case, it works perfectly. That is, it shows that on random data, our accuracy score is 0, which is exactly as it should be, what we would expect. Hope this has been helpful. I look forward to hearing your thoughts in the comments below. Thanks so much.